In a previous video, we were introduced to the enthalpy of formation, the standard enthalpy of formation. In this video, we're going to learn how we use that to find the standard enthalpy of a reaction. So the example I've got here is 4 ammonia completely combusting, so this would be an enthalpy of combustion actually, forming 4 NO gas and 6 water. All right, so the way we work it out is these are the things being made, so they will have their enthalpy of formation calculated. These things are being unmade or broken, so we're going to subtract the enthalpy of formation of these, because that of course is being reversed as the ammonia is being broken. Now anything that is an element, so in this case we're talking about our oxygen, they don't have an enthalpy of formation value. And the reason for that is they're already an element, and the definition of enthalpy of formation is to form something from its elements at understanding conditions. So we completely ignore anything that is an element. In this case, the oxygen is not going to be needed to do this calculation, even though there are some bonds being broken in that. So we're given all the numbers that are given in orange here. So we're given the balanced equation, and we're given these 3 enthalpy of formation values. We need to take note of the number of moles of each of these in the equation, because they're going to be important when we do our calculation of the enthalpy of reaction. And in this case, as I say, it would be a kind of an enthalpy of combustion once we worked it back to being a single mole. So the enthalpy of this reaction as it's written is going to be the products, the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So hope I can fit all of that in the screen at once. So I've got that there are 4 NO being made, so I'm going to have 4 times 90.3 kilojoules per mole. I've got 6 waters, and in this case it's steam. Do take note of the state of matter, because if they give this as a liquid, you've then got to include something else, which is the enthalpy of vaporization, which we met earlier as well. But that's normally given at scholarship level, so we'll address that with those students separately. So I've got 6 of those, so I'm going to go 6 times negative 241.8, and I'm going to add those two values together. That is the sum of the enthalpy of formation of the products. The reactants, I've got 4 times this top value. I don't worry about the oxygen because it already is an element, so it doesn't have a value. So I have this here. So as I move down, then I can see I've got quite a simple mathematical equation here. My enthalpy of this reaction is negative 1089.6 minus negative 184.4. I do that and I get negative 905.2 kilojoules per mole. Now I know nothing in the equation had 1 mole of it, but this is still the correct unit for this. Now because everything was given at the start of the question to 3 significant figures, my final answer should be as well. So I then round that number off to 905, which is our 1, 2, 3 significant figures, and keep my unit there. So this is how we use enthalpy of formation to find the enthalpy of a reaction. We find the sum of the enthalpy of formations for the things that are made, the products, and the sum of the enthalpy of formation for the reactants, the things that we started with, and I go this number minus this number to give me my answer. Then I round that off to the appropriate number of significant figures, and in this case that would be 3.